Okay. Hi, everybody. Welcome to Burning Amp 2024 afternoon session, where everybody snores and sleeps after lunch, and then they get me talking to them about crossover design. I'm Scott Hinson. My degree is in electrical engineering. I don't have it with me. I'm sorry. In fact, truth be told, I've never taken it out of the envelope. I just looked to see if it had the right name on it. My talk is entitled Everything There Is to Know About Crossover Design. And then the sort of engineer in me kicked in and said, that's a clickbaity title and it's not accurate. So I decided to retitle it. Go ahead. And then I titled it A Lot of What There Is to Know About Crossover Design. And then the engineer in me really took over and said, okay, we're not clickbaity anymore. We don't have the advertising, the marketing value, and we're also still not honest. So we're going to make it honest, and I retitled it again. Go for it.
One weird trick.
What I can cram in an hour about crossover design. Okay. This one's accurate. It has no marketing value whatsoever, but it is accurate. All right. So let's go to the next slide. A little bit about me. I got started building speakers when I was 15 years old. That was years ago. It started with books like that. How many of us have that book? Right? A bunch of us, right? And how it's going now, I actually went to engineering school to learn how to do audio systems. And I did have a choice between Georgia Tech and University of Texas at Austin. And then I saw the cost of Georgia Tech being an out-of-state school, and I went to UT. Then I realized UT didn't actually really teach you anything about audio systems. Like, that wasn't a class. So I took signals and systems and power distribution and kind of made it work from there. These days, though, audio is a way overgrown hobby for me. My day job is I research. I'm the CTO of a nonprofit that researches renewable energy integration into the grid. We get like 22 billion data points a day, monitoring houses nationwide. But I have never stopped doing audio stuff. So over the years, this is a set of subwoofers I designed during the pandemic. This is the pair that the Dallas Cowboys bought for their practice facility. And I have licensees of this design. They're all up and down the East Coast, knocking alcohol bottles off the shelves of clubs. This is the first year I came to Burning Amp. This is my third year. These are the speakers that I brought. This is another design that I've done. Next slide. If you want more information, I have a Facebook page, and I'm starting an actual web page because there's some people that are not on Facebook, and I understand that. Go to my Facebook page. I now have 75 plus articles, something like 1,800 pages of stuff written up, technical articles, complete designs, things like that. Some of it ranging from very basics to very advanced things like, I took that, oh no, I still have it. Very advanced things with titles like minimum phase, linear time invariant systems for, that likes to roll off people's tongues, right? Good stuff, right? Next slide. So, how do you design a crossover, right? There are tables you can find in books. There's website calculators, and these website calculators are very popular. I see people do this all of the time. And as I said, this is my third time talking at Burning Amp, and I'm going to probably challenge some strongly held assumptions in this talk. So therefore, it might be my last time talking at Burning Amp. But I have reasons for challenging those assumptions, okay? And I'm going to try and back that up with plenty of measurements and things like that to show why I have the opinions that I do, okay? So I went to this website and I put in, I would like a second order Linkwitz-Riley crossover at 2,000 hertz, and it spit out, and I told it I had 8 ohm drivers, right? It's what we normally buy. And it spit out this schematic and these crossover parts. So basically 5 microfarads and 1.27, so 1.3 millihenries, okay? And notice that the capacitors in the tweeter circuit and the woofer circuit are the same value, and the woofer circuit inductors and tweeter circuit inductors are the same value. That is my first clue that the crossover is a textbook crossover, and it is not working, okay? If I see those same values, okay? Next slide. So I did some more Google searching, and I found a fancier online calculator. And this one plots a frequency response for you, probably giving everybody a false sense of confidence that it's actually working. And I put in the same parameters, and lo and behold, I got the same answers. Okay, that makes sense, right? Those are equations that are well established, so you should get the same values. But then I noticed that it had a disclaimer here down at the bottom. So next slide. If you zoom in on that disclaimer, it says, and I hate reading slides to people, sorry, but I'm going to do it because this is a bit of an eye chart. The dB scale used is relative and not an indication of actual SPL. At this time, the response graph does not take into account variation in voltage or power due to load impedance. And then at the bottom, summed response ignoring phase. Okay, there's a lot wrong there. That's like saying, I've done your taxes, but I don't know how to do taxes. Okay, so let's go to the next slide. So what I did was, and I've written this many times, and it takes like a paragraph to write up, and I won't try and repeat the paragraph of all the errors that there are in what I call textbook crossovers, those formulas that you get out of books or on design tables, or what these online calculators generate, right? So what I decided to do was do a graphical version where I walked through the error tolerance and stack up of how those errors come into play and how big they get as you add each step. And then at the end, I show you the full error. Okay? So let's go to the next slide. So what I did is I went to Sound Easy, which I love as a program, but it, like my original title, is inaccurately named. I love it. It's great. It's the best functionality you can get for the price that you pay for it. But I usually, when I put it in print, add the words "not so" in the middle, because it is not easy to use, right? So I call it Sound Not So Easy. I love Bodan. He's great, but come on. There's some features in that software. I'm like, oh, why is it doing it? Anyway, so I put it in there, and I literally did that schematic that we saw. The tweeter was in phase with it was positive polarity with the woofer. I put the values in, and the summed response has a huge notch at 2 kilohertz. Okay, so the first error is, some might think that, we need to flip that tweeter around, and in this case, you do. I actually ignore the design rule tables most of the time on tweeter polarity. I let the response and phase tracking guide whether or not I have that tweeter flipped or not. I don't just blindly follow the rule. We'll get to that. We'll get to why in a second. All right. So yeah. Next slide. We're done with this one. So I flip the drivers around, and lo and behold, we have a nice flat response, just like the calculator, and yay, all right? But to do this, what I have done is I have created speaker drivers that are 8 ohm perfectly flat impedance and perfectly flat in frequency from 20 hertz, actually in this case 5 hertz, to 20 kilohertz. So they're perfectly flat for both. Are speaker drivers like that? No, they are not. All right. So next slide. What is the error if I use just the impedance? Okay. So I made new speaker drivers in the model, and I used measured impedance for the speakers that I brought with me here to the show today, okay, for both the tweeter and the woofer, and I left the textbook circuit in. And now we have over 6 dB of error in our response. Okay, so just the impedance results in 6 dB of error. You can see the summation. It is no longer flat. And if you actually had a speaker that had this EQ, this frequency response curve, you would turn it down in a hurry. Okay, because we're peaking right at 3 kilohertz. That's going to sound horrible. All right. So what's the next error that you might have, right? So let's go to the next slide. Speakers are not flat frequency. Now, some folks, and this is a valiant effort, there's many tools that you can use to extract the frequency response graphically and make a text file for it, right, so that you can import it into these programs. Some people will go to the manufacturer's data sheet, extract that frequency response information. Sometimes they'll even extract the impedance information, which again helps. It gets you a little better, but it is still not good. It is still not right. And this is why. This is the data sheet response in green, and I'm sorry for the folks with red-green colorblind. This is default colors. It was really hard to measure, but I'm going to point at it. This one, okay? That's the data sheet frequency response for the 10 CLA 64 woofer from B&C. Fantastic woofer, great woofer, love it. Budget driver, but works great. Again, we have these speakers right over here. Red is what I measured in that cabinet. Okay. The reason my measurement comes out nowhere near theirs is because we use very different methods to measure the frequency response of the driver. They're using either a very large baffle or possibly even an IEC baffle, and they're putting it in a large box. They are trying to show you whether or not the woofer cone is operating pistonically, whether, you know, what its breakup modes are like. They're not trying to show you what it's going to measure in your box because they can never know your box. Your box will always be different from their big flat baffle, right? So now, if you compare these two, we have up to 15 dB of error between the two, or difference between the two, I should say, okay? And my measurement includes baffle step, okay? So that is where if you put the speaker up on a stand out in the middle of space at high enough frequencies that baffle is keeping all the sound moving forward, and at very low frequencies that sound just wraps right around that woofer. So you have baffle diffraction loss is more accurately called, and it actually has baffle ripple in it, things like that. Whereas the B&C measurement doesn't have any of that because it's very different conditions, okay? All right, so we know it's not this flat. If we try and use this, we're still way off, all right? So next slide. Are we done with the errors in the textbook crossovers yet? Hit it again. Hit it again. No. Lisai, no, we are not. There is something called acoustic center, okay? Next slide. There's a lot of rules of thumb for acoustic center. They're all wrong, okay? They don't work. They are not accurate enough if you're actually trying to get the crossover to sum correctly, okay? Voice coil, where the voice coil meets the cone, align the voice coils. Are you aligning the front of the coil winding, the center? Where are you aligning this? Like you cannot use any of these rules of thumbs. It has to be measured, okay? If you are using something like REW, and because it doesn't have a loop back feature, it doesn't know when T0, well, actually it does, but it's hard to use. But if you're using it in its single channel mode where it doesn't know where the start of sound is, right? It has no time reference. What you can do is you can measure driver A, save that file. Measure driver B, save that file. Measure driver A and B in parallel, okay? They will add together. They will sum, they will make a new response. And then in your crossover software, you model A and B, and you start moving B back or forth in time until they sum to what you measured. You then know the acoustic offset very precisely, okay? And there's actually a tool in REW to do this. There's a measurement alignment tool that you can pull up, and you have 3 measurements, and you're moving them back and forth in time, and you find out how much you have to move one driver versus the other in order to have their references be aligned, okay? So And then you can actually use, as I said, REW does have a loopback version where it does know where t equals 0 is. I like to use ARDA. They stopped making it, unfortunately, so you can't buy it anymore. But I use ARDA, and it's a 2-channel measurement system with a loopback internally, so you know where t equals 0 is, right? And in that case, I can just directly measure it. I don't have to guess by moving these lines. I know where that impulse is and where it started and where it stopped. So next slide. How much error is that? Possibly. A lot. It can be a lot of error, okay? So I went back to, I took the impedance out, okay? I still don't have the actual frequency response of the drivers in. All I have done is moved the, and most times for like if you've got a dome tweeter and a cone woofer, right, the woofer is behind the tweeter, okay? In the speakers over there, I've got a horn tweeter and a cone woofer, and the horn tweeter is deep enough that it moves that tweeter back, so the tweeter is actually behind the woofer, okay? But it's actually about the same amount that normally a coned woofer is behind it. So the error is about this much. It would just be on this side of the plot, right? You can have 6 dB of error just because of that, okay? They won't sum together properly. All right, next slide. Are we done now? This is my kid talking. Are we there yet? Right? She's 16. She hasn't done that in years. Mostly there are other issues that I'm not going into here, right? So you can talk about driver compression. There's all sorts of stuff. There's nuances about how far away you're measuring. Like if you really want to understand the full impact of baffle diffraction ripple, you have to be 5 times the longest distance on your baffle, so that's usually diagonally. So if you have, a speaker that's that diagonal is 1 meter, and that's pretty easy to do with a tower speaker. You have to be 5 meters away to measure to get that full impact, right? And that means that, I never measure at 1 meter unless I've got a very small speaker. I'm always measuring farther away. You then run into the problem of if it's a dome tweeter or something like that, you've got a very large speaker that you might blow the tweeter up because you have to be so far away, you have to play that tweeter so loudly, right? So there's a bunch of juggling that you have to do. There's always compromises. You're never quite perfect, but you're struggling to get there, right? Another design style, and this little paragraph here is about all I talk about it here in this presentation, is the by ear. And usually what people do on this, what I've seen done most often, is they start with one of the textbook crossovers. It does not sound good to them. And they start tweaking the values until it does sound good. This can have disastrous implications for impedance. I have seen people start to move the tweeter crossover down, the woofer crossover up, and now they're playing both in parallel. And I don't know this for a fact. This is hearsay, complete hearsay. But if you look at the original impedance for the original Wilson Audio Watt, it is an amp crusher. It has a dip to 0.2 ohms. Okay, and I have seen by ear crossovers do this. So I don't know if that's what he was doing at that way back when, but I have seen this done. Okay, and what typically happens is somebody is designing that crossover to a couple particular tracks that they like because they're not taking these measurements. And then if I take a frequency response measurement of that speaker, I can very quickly go find a track that sounds horrible on those speakers because I know what is wrong, right? So I highly recommend being able to make those measurements. I see people do this all the time. They spend hundreds and hundreds of dollars on drivers. You can go for $99, get a UMIC 1. For $100 and something, get a Dayton Audio test system. You can measure frequency and impedance for $200. It's less than the cost of one really good woofer, and you can do this really, really well, all right? The technique is hard. It will take you a long time to learn that technique, but once you have it forever, all right? Next slide. So, what I meant to do for this show was build both sets of crossovers and have a box so you could switch them. The problem is that the textbook crossover sounded so horrendous that I wasn't going to subject you to it. I was running out of time anyway, and I was like, the last thing I need is for somebody to leave it in the textbook mode, walk away, and everybody's like, "Ah, these speakers Scott's design sound horrible," right? Like, so I didn't kill myself to stay up all night to make this. This is the textbook crossover result for the speakers that are over there versus what I designed, which is in red. Okay? This speaker sounded horrendous. It sounded horrible. It was every bit as bright and nasal as you might expect it would be. Okay? Next slide. It had a secondary fault in it that the total frequency response is not going to show you. But when you look at the frequency response of the individual drivers, it becomes very clear. They overlap for almost an octave. Okay? So both drivers are contributing to the output of the speaker, which means as you, especially vertically, as you move slightly vertically, you're going to get vastly different responses. And it's going to, and the off-axis response is going to be very, very weird. And what I have seen here is that as you get this better and better, there actually is a point where you're like, oh, this is kind of magical imaging. It's very ethereal and things kind of dance around, but it's not really accurate. Okay? And then it gets old after a while because your ear isn't used to hearing sound that way. And you are kind of fighting nature, and it gets tiring. And it is one of the things that I see in speakers, when I see this in speakers that have even a flat frequency response, it contributes to a lot of times to what people term listener fatigue, okay? And you end up with a acoustical crossover point an octave lower than your desired. So that was supposed to be 2 kilohertz, it's 1 kilohertz. You have plus or minus 9 dB from 40 hertz. Okay, next slide. So let's look at the schematic comparison. And I even helped it out by putting a pad on it, an L pad, because the tweeter is more sensitive. So it wasn't the pure textbook. I even gave it an advantage. The pure textbook was so bad. The actual crossover that I did has 19 components in it, okay, versus the 6 components for the textbook. And this is desirable for many people. They think they want fewer components until they really understand what that gets them, which is not a good result. All right, next slide. So what does it all do, right? What could I possibly be doing with 19 components in there? So I went through and I circled sections, especially on the woofer. When it comes to the tweeter, we kind of do it all on one slide. So first things first, there is a lower bass equalization circuit. So this is a parallel RLC. Remember that the textbook inductor was 1.7 millihenries. I don't have a single 1.7 or 1.38 millihenries, something like that. I don't have a single one of those inductors in this circuit, right? So I've got 5 millihenries, 12.5 ohms, 10 microfarads. Next slide. Without the EQ, with the EQ. This was a very, very chesty, vocal forward, boomy kind of speaker. All right, next slide. Second order low pass, but that gives me effectively a 4th order acoustical. All right, next slide. I am not a fan of using Zobel networks on tweeters. I think they're a waste of money. I can get the same response without them most of the time. I am occasionally a fan of using them on woofers, and this is why. I have one here to cancel. It's a vented box, so it has 2 impedance humps. I have one here to cancel the upper impedance humps, and this is why. Next slide. If I don't have it, it's the green response with the huge peak. If I do have it, it's this red response, okay? So all of those components are necessary. I can't take any of them out and come anywhere close, all right? Next slide. So this one, as I said, I sort of circled them all. Second order high pass, I did a pi attenuator. This is a resistor in parallel, resistor series, and another resistor in parallel. What this helps me do is this crossover, no matter what I hang on this side, sees the same impedance. Okay, you can only do this when you have a tweeter that's so much more efficient than the woofer that you can get away with this. Normally you have to do the L pad, right? And then you're adjusting everything at the same time, and it's kind of annoying. But in this case, I could adjust this side independently of this side. And then I have 2 high frequency shaping filters up here. Next slide. No high frequency shaping, high frequency shaping. Okay. So all of those parts are needed. All of those parts are needed. All right, next slide. Here's another real world example. This is a two-way speaker I did, and I want to say I used the, oh, I don't remember which, I won't say which speaker I pulled because I don't remember which speaker I pulled. It's one of the DIY RM examples. What I wanted was this nice slope here, this nice slope here, a nice big triangle of integration region here so that the drivers aren't fighting each other, they're getting out of each other's way. But these electrical responses have nothing to do with any textbook curve. What I wanted was the textbook curve to be in the acoustical region, not the electrical region. Do you know what this is called? This is called EQ. I'm applying EQ in my crossover permanently to these drivers. All right, next slide. Okay, so I'm also going to talk about parts for passive crossovers. Okay, parts is basically parts. We've got good parts, gooder parts, and some okayest parts. Okay, hit it again. I've got a little animation here. When I talk about capacitors, I buy basic poly caps for most of my speaker crossovers until the value gets to 10 to 20 microfarads, somewhere in there, and then I switch over to bipolar electrolytics. Unless I am designing a very high-powered PA speaker and I need that voltage rating, right? Okay, next, hit it again. Resistors, I'll get to this in a second. I basically buy any power rating resistor that I can find, but we'll get to that in a second. Next, hit it again. Air core inductors are great, okay? Problem with air core inductors is they tend to have relatively high DCR values. Hit it again. I really like steel laminate core inductors, okay? Especially for larger values when I need that DCR to stay low. And then hit it again. What I don't like are potted core inductors. These are distortion generators, and when they saturate, they sound like amplifier hard clipping. Okay, so do the laminate core inductors. It's way harder to do it for those. All right, so hit it again. So let's talk about this. I hear this a lot. I have seen many a video where somebody says you need to put a small value cap because it's faster. Okay, run away, just run away. That is not true. I don't use them. I just don't. Hit it again. I just don't. Again. But why? Okay. What I want a capacitor to be is capacitive. Okay. And if you plot impedance versus frequency, you want that line to be relatively straight. All capacitors have what is known as a self-resonant frequency. Okay. When I buy a capacitor, when we buy capacitors, we get some other parts in there for free, and those parts all suck. They're all, you don't want them, but you have to have them. They come with the physical package of the capacitor. So what happens is when you hit that self-resonant frequency, after that, that capacitor is actually inductive. Okay? So what I did is I pulled, this is off a data sheet. I think this might be from Vishay. I don't remember where I pulled this. I pulled this years ago. For film caps that are similar to the construction that we typically buy for loudspeaker crossovers. And a 35 microfarad cap has a self-resonance frequency of over 100 kilohertz. In a speaker crossover, if you're putting 100 kilohertz out there from your amplifier, there's something wrong with the amplifier. All right? Okay, so, and it is still capacitive where you need it to be. So next slide. So what I did is and I think there was a talk earlier, I missed it because I was building speaker kits back over there about Spice, right? We had a talk earlier about Spice, did we? I think we did. Maybe that was last year. I don't know, I've slept since then. What you want, as I said, is you want that impedance to be dropping. If it's not dropping at that rate, it's not a capacitor. Okay, if it's dropping faster than that or slower than that, it's not a capacitor. So what you want is this, yay! Then you hit your self-resonant frequency, yikes, no good. And then, ooh, we've gone inductive, right? Okay, next slide. So that is a 35 microfarad cap. And then what I did was, since I have this in Spice, I modeled it with a 0.1 microfarad Perfect. Absolutely perfect bypass cap. There's no strays, nothing, okay? It goes, yay! We were already yay in that frequency region. We were already good. We haven't helped, okay? Boo, we have our self-resonant frequency. We've gone inductive and then woo! Now you have a second RLC circuit to resonate. Then it goes capacitive again, which is yay, but it's pointless because it's well up here at 5 megahertz. And again, if you have an audio amplifier broadcasting at 5 megahertz, you have another problem, all right? That's bad, okay? Next slide. So then I put and said, all right, another way to visualize this is let's just put that perfect cap here. Its impedance is so high compared to the 35 microfarad, it's not helping you. And even if it did, if you ignored this, it would, as I showed in the other graph, it would really only help you way up here. If you have a real 0.1 microfarad cap with the lead length like you do in an actual circuit, it moves that secondary resonance down even lower. And if you're clipping these things in with really long leads to try them, you might actually be able to get it down to the point where it's in the audible range. Okay? So beware of those bypass caps. All right? Is that new for everybody? Is that new news? They're important. They're real in digital circuits. Like I used to design RF cable modems. I used to design RF systems for RF diathermy, where you're heating the iron molecules in the blood. And I had to use bypass caps all the time. And even in those circuits, I see a lot of engineers deploy them wrong. They put the biggest caps near the pins, and then the little caps are far away. And even that on that tiny printed circuit board, that much lead length is enough to ruin the effectiveness of that bypass cap. And so what you end up having to do is, if you do them right, either the nearest or they're on the flip side, and you have some very special via structures to cancel the inductance and all this stuff. So it has to be done very, very specially. They're a real engineering tool, but I don't use them for crossover designs. What I will use is values when you know those high frequency notch circuits, if I have a very high Q speaker peak, the Seos magnesium cone woofers typically need this. They can't control that woofer, that frequency accurately enough. So sometimes I have to tune that, and it looks like a bypass cap because I'm adding 0.1 microfarads at a time, but it's not. I'm just trying to hit the value I need, right? But it's not a bypass cap. And especially on woofer circuits, like there's just no need. Like those things were all up, and the benefit was all up in the 10 megahertz region. You've got a 2 kilohertz crossover, right? All right, next. Impacts of inductors, and I'm going to watch the, oh, okay, we're good on time. Impacts of inductors. Series DCR can detune your base alignment. So a lot of folks make this mistake. In their simulation software, they simulate what their box alignment's going to be. They put the teal small parameters in, and they simulate it, but they don't add the DCR that's likely to be in those inductors for that low pass crossover. Okay, and this can detune that alignment fairly significantly. So I usually just add a 0.3, 0.4 ohms just to kind of cover myself, right? And that's good enough, because if it's 0.5 or 0.3 and I've put in 0.4, okay, it's going to be a little different, but you're going to see more difference by just driving that woofer harder, right? The parameters will change. Even low DCR inductors impact damping factor. Like we specify amplifiers and we get all excited about a high damping factor. I don't pay that attention to that anymore. All right, hit the button. Example, a really expensive air core inductor, or even a iron laminate core, will have a DCR of 0.2 ohms, okay? Which means, by definition, hit the button, automatically your damping factor is no better than 40. Okay, so you can have a 2000 damping factor amplifier, you put that DCR inductor in front of it, and your damping factor is down to 40. I don't worry about damping factor until it's single digits, honestly. And when I do PA system work, there's folks that work with me that want to do passive systems, and then I'm like, okay, well, where are the amplifiers going? And they're like, well, they're going over here, and I'm looking on the architectural plans, and I'm like, that's 400 feet away. No, because now we've got a damping factor of 0.8. Like I just can't buy you big enough wire to do this. We've got to get the amplifiers closer. You have to go active, right? Which gets the amplifiers closer. All right, next slide. I worry more about intermodulation distortion, okay? And I see a lot of sort of consternation and talk about this, but I haven't always seen a lot of measurements. And me being me, I just went and took them. Next slide. So the way I tested it is I did a multi-tone test, okay? And so the first thing I did was test my amplifier into a test load, okay? And so what we have is the signals that I wanted, all these tones, these big tall tones, okay? And the noise floor of the measurement system is way down here, and this scale is large. It's like 145 dB. And so this is the noise floor of the measurement system, and this is what the amplifier, all this extra little hash in between these tones, and you can see discrete tones here, right? That's stuff that the amplifier generated that wasn't in the signal, okay? That's in this. If I just loop back the sound card, you see much lower levels of it. You can see them in red here, okay? So next slide. This is an air core inductor compared to the amplifier. Pretty good, right? Makes sense. You're not going to get a distortion component out of an air core inductor. This is the answer we want. Had I not gotten this answer, something would have been wrong with my test setup and I would have needed to go back and start over, right? So next slide. This is a laminate core inductor compared to the resistive load, which is the amplifier itself. And now we're starting to see a little bit more stuff peek out here, these green lines. So we've got a little bit more hash. So the laminate core inductor is not as good as the air core. Again, I am okay with this right now. This is the answer I expected. But the thing that we have to remember is we have to put that into context. All right, next slide. This is a potted core inductor. This is a ferrite potted core inductor. Not only is it much higher in level, but at higher frequencies, there is a ton of cross products in there, okay? Because there's a hysteresis curve and all sorts of, and saturation, there's all sorts of stuff happening in here, and you don't want this, okay? This is why I do not like these, okay? Next slide. Even though a woofer is typically way worse, and this is the context that I was talking about. So I put that same signal into a woofer, and look how high everything is. Go back one if you can. Can you do that? All right. The catch is that the P core, the potted core stuff, there's a bunch up here at higher frequencies. Go to the woofer again, forward. And you're not getting it as much. So if I overlaid these, and I was sort of running out of room, I had like 48 slides to get through in an hour, so I had to go quick. Right. Next slide. Go back to, this is the laminate core again. Okay. See how much lower it is than the woofer, right? This was a 12-volt RMS signal with 1, 2, 3, 4, 5, 6. I think it was 20 tones, maybe 12. I forget. However many spikes there are, that many tones. And I want to say it was like 12 volts RMS. This was shockingly loud, and this sounds horrible. This is a god-awful sound. It makes you want to run from the room. I had in-ear protection on, I had over-ear protection on, like, oh, this is bad, right? And yet, the laminate core inductors are an order of magnitude better than the woofers, except when they're not. We've gotten to the point, there's a couple of brands these days, Purify being one of them, and some of the newest Seos graphene, some of the newest 18 sound motors on the Pro Sound side, some of the newest SB Audience on the Pro Sound side, at lower volumes, start to get down to this level of performance, okay? So it is getting to the point where we have woofers that are starting to approach the level of higher distorting amplifiers even, right? So 0.2, 0.5% distortion, even 0.1% distortion on a woofer can be achieved at low enough volumes. And when I say low volumes, it's still perfectly listenable. We're not talking like super quiet, right? All right, next slide. Resistors. I have seen many a video where somebody talks about sand cast resistors sounding, wait for it, does anybody want to say it? Grainy or gritty, right? I wonder how many of those people have ever opened up a sand cast resistor. It's a wire wound inside, okay? Most of the time, actually all the time, but, and it's not sand, it's silica. It's there for a reason. It is there so that if you burn this up, your whatever you've got this thing in doesn't catch on fire. All right. It is very, very precision made. It is not like they're going to scoop and beach sand. No, they have to mix it with the right epoxies and all sorts of stuff to get this thing. But that is what is inside of that. And I tried to, and I didn't have the picture. I just left the broken part there. I tried to take one of these apart. This is a metal film. It's very similar construction. But a lot of times it's a film that gets wrapped around. There's actually versions that look like this that have very similar construction inside. But this is what's inside here. Okay. So as long as the self-inductance of this resistor is low enough so that it's not changing value on it in your crossover circuit, it's fine. And you have to work hard to find an inductor. All right, I'm sorry, to find a resistor that is inductive enough to be changing in your crossover circuit. You really do. It either has to be a very large value, which means it's probably not doing all that much in your crossover circuit, or it has to be very, very poorly made. And they actually have windings. It's like Ayrton Perry windings that are non-inductive winding, where they sort of double back on each other and cancel the magnetic fields. So that's what they mean by non-inductive. But this is what's inside of this. And I use these all the time. I will occasionally move to these if I want it to look cool. And there's some other ones that I will move to when I need super high powers, or it needs to go on a printed circuit board for a certain reason or something like that. But for my point-to-point crossovers, I just buy these because they're cheap and they work great. Okay. Next slide. Thank you. That was it. I have 10 minutes, well, 10 to 12 to 8 minutes of question time. If you want to get a hold of me, any of these things, I have a website coming soon with my new logo. Hopefully that came across today. My wife hates DIY RM as a marketing tool, but when I told her that this, she's like, well, what is your whole shtick? And I was like, speaker science and sarcasm. She went, oh, if you don't make that your slogan, you're dumb. I love my wife. All right, questions? Yes. Yeah. That is Charlemagne, and he is judging all of us right now. This is the king of the household, and I have another picture of him recently. He wanted cheese off my daughter's salad, and he just got up on the stove in one of the pans, so he's just sitting in the pan looking at us. So, get off there. Anyway, are there any other questions? Besides Kat, I see one in the back. Yes.
Like any driver by a lot, like mostly resistors are like 10 watts, 15 watts, and like I feel like I need like 100 watts potentially power.
What driver are you attenuating? Like, are you attenuating a woofer?
So, I do, yeah.
Okay. Okay.
Yeah, so.
Right. Okay, the tweeter. So the thing to think about is that the power spectra of music is such that it's decreasing with frequency. Okay. And so long term, like that 10 watt resistor will handle 50 watts for 10 seconds and 500 watts for a second and stuff. Like it will handle a tremendous amount of power and be just fine for short term peaks. It's the continuous that heats it up. Like a 1-inch dome tweeter, I have a paper on this on the website, a 1-inch dome tweeter, I cooked the ferrofluid off of it with a 5 watt continuous signal, actual real watts going into that voice coil. That was a 100-watt rated tweeter. That power rating is in system after a crossover. And so you probably don't need as many watts in those resistors, continuous power dissipation as you think. I've done 1,000-watt handling DJ monitors with 50-watt resistors in them, which are pretty easy to buy. Does that answer the question? Okay.
As I listen to this, I feel compelled to hook an amplifier to each driver and do whatever I do for crossovers ahead of the amplifier. So I'm just curious.
So it doesn't. I have, again, on Facebook, again, I mean, I was already at 48 slides, so I couldn't do this. If you do active crossovers, okay, you still need to do that EQ part. Otherwise, you end up with the exact same problem. Like, you can't just get, like I don't like analog active crossovers, because then you basically need to have a graphical equalizer for every driver, if you're going to do it that way. Or you have to figure out what your EQ is and build EQ circuits. And like Linkwitz does that. Like he did that with all of his circuits. You saw his, okay, well, I had this peak and I needed a Q of this, and he does that. So that is the way to do it. I much prefer these days because, what's the word? I'm lazy. And DSP is cheap enough and powerful enough, and the DACs are so good these days that I just buy a like a $450 DBX PA2. The Pro Sound world has like the real Pro Sound guys, like the stadium sound guys, that is not acceptable for them. Right, it doesn't have all the bells and whistles, but for anybody, unless you've got 10,000, people in your auditorium and you've got delay lines and delay stacks and all this stuff, it's a fantastic unit. It's quiet. It has a ton of EQ bands on every output. The limiter stinks, but again, you're probably not going to end up using that. And I just use one of those. I have 3 of them at home right now. So I do it actively all the time, but that means that you then have the complication of amplifier per driver and all this other stuff. And sometimes I just want the ease of just plugging in the speakers and going. Other questions? Yes.
The speaker you 40 hertz.
Yep.
Got there in that sealed box through.
No, the gray speakers. Those gray speakers are vented. Those are ported.
You said there's like
yeah. Well, I'll show you. Basically, my low pass crossover starts cutting in at like 60 hertz. So that woofer's going like this, and I start doing this with the crossover network, and I've got that EQ circuit to take a notch out of it as well, so that I'm literally just using the crossover to tilt that upward facing. You remember how the woofer had that upward facing response, that upward sloping response? I just tilt the whole thing down so it's straight. And now the crossover equalization is what allows me to get a 40 hertz F3 out of a 70 hertz FS driver in a vented box. Yeah, it's not even at the cost of power. It's at the cost of voltage headroom, because the components that were doing it were inductors, so they're reactive. They don't actually absorb power. They just put, this is getting into the electrical engineering weeds, right? But they put impedance in front of it that doesn't dissipate power. The only part of them that's getting hotter is the DCR, and you're just not setting that much current through them, okay? So they don't get hot. It's not power. It is a reactive impedance that's put in front of it. Sensitivity. Use the word sensitivity. Efficiency is the wattage. Sensitivity is the voltage. It's important because people are like I can get a driver that like at 2.83 volts is really loud, but if it's a 1 ohm driver, it's pulling a lot of watts. It's not efficient, but it is sensitive. Conversely, I can have a 32 ohm driver that gets fairly loud, right? And it's not sensitive, but it is efficient.
Did you do paper on the site?
I did. It's like 30 pages. So I type a lot. Yes.
You see some of these things talking about adding passive parts in the crossover with the idea of lowering distortions.
Oh yeah. In fact, that one blew my mind. I'll be honest. The first time I saw that, I was like, that can't work. And then I tried it, and yeah, it does. So So it is, it's twofold. There's two things happening when I really studied it. What's happening is that when something goes into resonance, it does not take much energy to get it to go and keep going, right? So a resonant system, you barely need to activate it before it starts to go, okay? And if you put a notch filter at that resonance and just suck all the energy out of it all the time, it actually helps the driver over a larger bandwidth than just that resonance. Because if you've got a driver that's resonating at 3 kilohertz and third order is that's the third order of 1 kilohertz, it actually helps your THD figures for the driver at 1 kilohertz. Okay, so it does work, and it's a valuable thing to do, and it's something that I have kept in mind. I just haven't had a chance to put it into application for a system where you may do an active system and put that filter to knock that energy out of that woofer. In that case, you wouldn't want to do a parallel shunt because you would short the amplifier out, but a series parallel circuit in front of it to keep that energy out of there. That would actually work, yeah. The other thing that can happen there is that, I'm going to blank on his name, Andrew Jones pointed me at this paper. Was it Vanderkooy? No. There's somebody in AES that went to all current drive systems, because if you don't have distortion reduction features in the motor of your speaker and you drive it as a current source, you can actually reduce the distortion. These days, I went and tried to replicate it out of curiosity with very low distortion drivers that have like the shorting, the Faraday rings and stuff like that, and the pole caps and stuff like that. And it's just not as effective anymore because those features are doing the job. Yes.
Inductor distortion versus level. Does it? Do you hear a point and it goes crazy?
Yes. Yes, you do. Yes, you do. So any chord inductor, when it hits saturation, it's game on for distortion. I mean, it's going to be bad news. You know, in practice, a lot of those the manufacturers will say, like Urs will say, this is a 500 watt super Q. Well, that's probably the max system rating that I would plug on that thing.
Okay, so if you're looking at the power ratings for it, and you're
it's such a it will change so rapidly depending on how you're driving it. Like if I've got one of those systems and I'm putting a very high level, very low frequency tone through them, that will saturate that core much easier than like a 30 hertz versus 300 hertz, right? That will saturate that core much more easily. And so but with music, when you're talking actual music instead of test tones, those 500 watt rating, 250 watt rating from the manufacturer, like the Dayton, 18 gauge coils, I think they say are like 200 watts. All right. Yeah, you're just about right. Yeah, I have rarely paid. Most times the woofer is telling you turn it the bleep down long before the inductor does. Right. All right, I think we're getting close to time. I'm seeing the hook coming. Thank you, everybody.
Thank you, everyone.